All right, last topic for this chapter is Kepler's laws. And I've stated the three of them, all three of them in kind of a mathematical way. If you Google Kepler's laws, you might not necessarily find exactly these mathematical expressions right away. And I've also pre-drawn some pictures here on the whiteboard that I'm going to use to help explain what each of the three of these mean. So the first of Kepler's laws says that orbits are in the shape of an ellipse. In other words, orbits are elliptical. I've written here a fairly standard version of the formula for an ellipse that you can look up in math books. If this is the graph of an ellipse on an xy axis, one way of thinking about this is that there's these parameters a and b here in this formula, and it turns out a corresponds to where the ellipse crosses the x-axis. Actually, it crosses at a and also minus a. In that sense, as a point, this would be like the point minus a0. This would be the point a0. The parameter b has to do with where it crosses the y-axis, and so in that sense, like it would cross here at the ordered pair 0b, and then down here there'd be the position 0 negative b in the Cartesian plane would correspond to this crossing point down here. And so that's kind of how you can relate the a and the b in this formula. And it kind of makes sense, because if x is equal to 0 and y is equal to b, this would be 0. This would be b squared over b squared is 1, which works, right? And that kind of, you could test that for all four of those points where it crosses and see that that works. Anyways, I think we'll see an example where we'll explore in a little bit more detail some aspects of the equation of an ellipse, but this class is not necessarily meant to be a full review of the mathematics of conic sections, but we're just going to touch on it a little bit. Let's move on to Kepler's second law. Kepler's second law, I've written there is delta A over delta T is equal to a constant. And boy, that's an interesting statement. That's one you probably wouldn't necessarily see that commonly. The way I would describe that is that represents a rate at which area is being swept out. So if I have a planet in this case, highly elliptical orbit, and or some other body, maybe it's a comet even, you could say, and this is, whatever it's orbiting around, which if it were our solar system, that would be the sun, right? If the planet at some point in time, say, goes from here to here, and that's in some like let's say time interval delta t, and then later in its orbit it's orbited way out at the far end, and you ask, like, how far does it go in the same time delta t? It'll go less far. It's slowed down out there. That's kind of the deeper meaning of Kepler's second law. But the way Kepler's second law kind of phrases it is, if you look at this area right here, so if you say, like, what is the total area swept out? In other words, I'm talking about like this area right here, swept out by that planet in that time delta t. If you take the area that it sweeps out at another part of its orbit where it's farther away, it's going slower there, but the area that it sweeps out in that same amount of time delta t will always be the same. So in order for these two areas to be the same, it basically means the planet must be going slower out here because this radial distance has increased. And in that sense, if you say, hey, delta A represents either of these two areas and delta t represents the same time, then delta A over delta t would have to be a constant. So that's, again, how that is expressed in mathematical form there. Now, we've already seen Kepler's third law. That's the one that says orbital radius cubed is proportional to orbital period squared. And the way to kind of think about that is Kepler's third law is comparing different possible orbits within the same system, or you could say solar system in particular. Basically some system with some center of, or gravitational source, big source of gravity, like a sun or something like that, right? And like, if these are two different orbits, like if there's like an orbit 1 and an orbit 2, and you say, well, how can I relate that to this proportion? You could also express that as ratios, right? Because all proportions, you can do that. So you could say, okay, r1 cubed over r2 cubed should be equal to t1 squared over t2 squared is kind of an interpretation of this proportions. But again, it's really about comparing planets in different sized orbits. And one of the ramifications of it is that planets that are closer to the sun, or whatever thing is the center of this solar system, they're going to have to move faster. So that's something that's kind of embedded within the mathematics of this statement.